All right, so this time we're doing the lawn roller problem. Here's what we know. We got this lawn roller. We're going to pull it with a force applied to this thing that they call a yoke, right? It's basically a handle. And the question is, what is the biggest force you can apply here so that it rolls smoothly without slipping? The idea is if you pull it too fast, it'll just slip. There won't be enough frictional force to make it rotate. And so the problem tells us that our coefficient of static friction is 0.7. Okay? And so the idea is we want to maximize our static friction to maximize the torque that causes the wheel to rotate about this center thing. So this is actually the one problem where you can actually assume that your friction is at the maximum, right? Because if it's not, you could make it roll faster, right? Okay, so let's go through and make our free body diagram. So I've already indicated two of the forces here. So your gravity is going to be 80 times 9.8, because that was your given mass, so that's 784 newtons. You're going to have a normal force, also 784 newtons. So now I can find my maximum static friction just by multiplying my coefficient times my normal force. And the maximum static friction ends up being 548.8. Oops, let's try that again. 548.8 newtons. All right, and then, yeah, we're looking for F. All right. So again, this is a net force equals net force kind of net force equals net force, net torque equals net torque equation. So I'm already noting that if I do a net force equals net force equation, I'm going to have two unknowns, right? Because I don't know my force and I don't know my acceleration. Okay, so that leads me to think maybe we should start with net torque equals net torque. All right. So when you do that, the logical choice is to choose your pivot point where your unknown force is. So that's what I'm going to do. I'm going to go ahead and do net torque equals net torque, and this time I'm choosing my center of mass as my pivot point. This is unusual, right? Usually I pick the pivot point at the bottom. The reason is because usually I don't know friction, but I do know the applied force. This time it's the other way around, right? Okay, so let's see, net torque. So that's I times alpha equals the torque, the only force providing the torque now is friction. So that's my force of static friction times my radius, right? So let's plug in our numbers. Let's see, we've got 1/2 mr squared. How's the red? Can we see the red? Looks like it's all right. Times alpha. My alpha is just going to be A over R. Equals, notice we have to do A over R or our radii will not cancel. And then static friction is 548.8 times R. Okay? So all of those R's are going to cancel. And so what you discover is that A is... Oh, shoot, I know mass, don't I? So I could have... Here. So this 1/2 m here should have been 1/2 times 80. Right? So now you can solve for your acceleration. And it actually ends up being a really big acceleration. You end up getting 13.72 meters per second squared. So that's the largest acceleration we can give this thing such that it still rolls. All right, so our acceleration is going to be 13.72 meters per second squared. All right, so now we need to find out what force will produce that acceleration. Okay, so now I'm just going to do net force equals net force. We're almost done here. Look at us go. Net force equals net force. So, mass times acceleration equals force minus friction. Solve, your force ends up being 1,646.4 newtons. Give or take with some rounding, yeah? All right, there you go. Problem number 7. Done.